Good morning, class. Welcome to day 27 of grade 11 Coronachem, also for 12 college. This chapter is called Chemistry of the Environment. It is a controversial chapter because there are many parties at work, many interested parties. There are, on the one hand, companies that stand to lose a lot of money if they're forced to comply to overly restrictive laws. There are also, obviously, the common man, the citizens of the earth, who are subject to whatever is done to the earth, for good or for ill. And also there are governments who stand to gain or lose depending on how laws are written. It's something that I would keep a very keen eye on because I think that this is an area of great political interest. Not only of interest of air quality and land use and water use. There are laws being put in place which create a concern for the development of dictatorships in the form of government. And very often, to get a dictatorship, you can't just, well, I guess you can. The old-fashioned way is to do it by force. You come in and do it with weapons. But there are other ways of creating dictatorships, and one of them is by management by crisis. I just want you to look at things that happen in the world with more link side, with a little more suspicion than the average, simply because many of the laws that are being passed that are ostensibly to protect the environment can have other purposes which are less noble and which we should always keep an eye out for. And we should listen to what politicians are saying so we can fully understand what the real agenda is. Anyway, with that in mind, July 21st, 2001, in Bonn, Germany, 178 nations signed a treaty based on the Kyoto Protocols. USA did not. And yay, USA, I agree with that. Based on concerns for the environment and human activity. I'm not one who believes in pollution and that everybody should just go crazy and dump toxic chemicals into rivers. Don't get me wrong. But from there to signing on to a central governing authority that has tentacles spreading all over the planet, there's a happy medium somewhere in there, which doesn't involve developing a fourth level of government. And we see that April 1st in Canada, for example, we have an increase of the carbon tax. So right in the middle of the corona crisis, let's increase the taxes. All right. So anyway, one of the concerns that was around at that time in the 1990s was the release of chlorofluorocarbons, which are substances that were used as propellants in things like hairspray. And the reason there was a concern, it was a legitimate concern, was that the chemicals that contain fluorine and chlorine can go up into the higher levels of the atmosphere, and when they start hitting more intense ultraviolet radiation, which you get at those higher altitudes, simply because of the fact that as the atmosphere thins, less and less of the sun's rays make it. Which is a good thing, because if it wasn't for the fact that the atmosphere filters the more intense UV radiation coming from the sun, we would all die. It would kill the surface, everything on the surface of the planet. So our atmosphere protects us from those intense forms of electromagnetic radiation that are incompatible with life. The problem is that at the height of the stratosphere, which is where most of the ozone layer is contained, which absorbs the key wavelengths, you can get some of these chemicals that used to be used as propellants, and they are known to catalytically cause the breakdown of ozone. So some scientists were saying that our ozone layer was thinning and its filtering properties were diminishing, and so the ultraviolet radiation was reaching lower altitudes where it can do serious damage to your DNA and give rise to cancer and things like that. I don't know if I agree with all that because, in those intervening 10 miles of air, I'm pretty sure a high energy photon would be absorbed. So I don't know if I agree with the whole theory. I think that there may be something to it, but there may be other variables. The fact that we don't expose ourselves to the sun in the winter months, especially in Canada. And then when we go on vacation, what do? We take our lily white bodies and we lay on the beach for 8 hours. So the next day you look like a lobster, and there's where your DNA damage is happening. If you're going to go in the sun, do it, by degrees, bit by bit. Maybe the first day, especially if you're very fair-skinned, 20 minutes of exposure, and then increase by 10 minutes every day until you can stand outside the whole day. But even then, it's probably not a good idea to bake in the sun for 12 hours a day or as many hours as there's daylight. There's moderation in all things in moderation. And the sun is good for you. It helps, your body makes a whole host of substances that fight infection when you're exposed to sunlight. So it's good to expose yourself to sunlight, but again, always in moderation. Water is a good thing, but if you drink 8 gallons a day, you'll die. One of the other issues that comes up on the issue of chemistry of the environment is climate change. It's the mantra that everyone is yelling these days. Climate change, we got to stop climate change. Just pour chemicals in the atmosphere to block sunlight and reduce the global warming. And whoa, just take a minute here and take a step back. 10,000 years ago, the earth was blanketed in snow and ice. So climate change has always happened and will always happen because it's part of the natural cycling of climate. You can't stop climate change, and if you try, you would probably do more harm than good. Climate will change over the course of centuries, and usually this does happen over the course of centuries. We do have sometimes wide fluctuations. In the 16th century, the River Thames froze solid, and people were able to go skating and walk across it when normally that doesn't happen. So there have been times in the past when we've had cold periods. There have also been very warm periods. So it's not really, in my opinion, intelligent to get all worked up about climate change, because the natural variations that history has observed are exceeding anything we've seen in our own time. Yes, hurricanes happen. Yes, tornadoes happen. And some years they happen more frequently. If you want to be smart about things, don't build near the coastlines if you're afraid of hurricanes. If you have a valuable property, maybe build a few 100 meters inland and things like that. There are things that can be done to overcome all the difficulties that come our way. If you live in a tornado prone area, you build your houses with special clasps on the roof trusses so that they hold the roof trusses to the frame of the building, and then the building is anchored in concrete. You can have a concrete basement, for shelter. Your whole house might be swept away if the tornado is strong enough, but at least if you have a concrete basement, that you'll be safe in there. Things like that. That's how we use our intelligence to plan ahead, to think of all the possible contingencies. What could go wrong is the question you ask yourself in this area, and then you act accordingly. If you live in Canada, you have to live in an insulated building. You have to have air conditioning, otherwise you spend the months of July lying on your bed in the form of a letter X, not able to sleep because of the humidity and the heat, and so on. There are questions of air quality, land use, water use. All of these things are probably appropriate to regulate, but not to the point where people's liberties and private property is being encroached. This is something, there's a thorny issue in that area, and I wish more people would pay attention to it, because it's very easy to lose all your liberties under the guise of attention to the environment. And I'm very cynical in that regard. Feel free to disagree with me, but that's how I feel about it. Let me show you a few things about our atmosphere so we can talk intelligently. About the issue. The atmosphere's 4 lowest layers are: 1, the troposphere. And it extends from 0 to 10 kilometers altitude. Then we have the stratosphere, which extends from 10 to 50 kilometers. Then there is the mesosphere, which extends from 50 to 85, and then the thermosphere, which extends from 85 to 110 kilometers altitude. And beyond that altitude, there might be what we call the ionosphere, if I remember correctly, but there's precious little air above 110 kilometers. In fact, 99% of our atmosphere is contained within these two layers. So 99% of our atmosphere is here. And layer 1 is 75% of our atmosphere. So really, it's a very thin layer of air that covers our planet. And of course, as you go deeper into it, which is closer to the Earth, it gets compressed more and more. And that's why most of the mass of the atmosphere is at these lower altitudes, because if you look at the kinetic molecular theory, gases are compressible, and where the pressure is higher, the molecules are closer together. And of course, as you get to the very high altitudes, the molecules can fly a long distance before they bump into another molecule. They don't reach escape velocity though. To escape the Earth's gravity, you have to be moving at 11 kilometers per second. The average molecule at room temperature is probably moving around 400, 500 meters per second, so half a kilometer per second. So to get escape velocity for the air molecule to literally go into space, it has to be going 22 times faster than what you see at sea level. But there are molecules that achieve those velocities, typically lighter molecules. And also remember, as you get to the higher altitudes, there are zones in the atmosphere where the temperature tends to increase. It actually has a peculiar M-shaped temperature profile. It looks like this. If you look at the temperature, the graph of temperature varies between 170 and about 290 Kelvin. So 290 Kelvin is about 23 degrees, 290, 273, 27, right? No, about 17 degrees Celsius down to 100 below zero. So as you go as you're close to the ground, sort of made the graph backwards here, the altitude, here's altitude 0, altitude around 110 kilometers. So you see the points where there's transitions in the temperature are how the different layers are named. So the layer between troposphere and stratosphere is very thin. It's called the mesopause. And the layer between the mesosphere and the stratosphere is called the stratopause. And the layer between the stratosphere and the troposphere is the tropopause. So between here, you have the tropopause. You see it's where the inflection point in the temperature, where the temperature starts to change direction. Most airplanes fly at around 35,000 feet, which is about 7 miles altitude, about 10 kilometers altitude. So that's right at the juncture between the troposphere and the stratosphere, and the temperature there apparently is close to the coldest. I guess that's where the airliners get the maximum fuel economy. So the airplanes are very careful to fly at an altitude that will maximize their distance flown for the amount of fuel used, plus making compromises obviously with how fast you can fly. You can fly at full throttle, but you're going to burn a whole lot more fuel, and it cuts into your profits. I even heard recently in an article that some of the airlines are looking for women. They hire exclusively women because men are heavier and it uses more fuel to fly to a different country. I don't know what kind of discrimination that is. It's a weight discrimination in addition to gender discrimination. But it makes sense. I mean, if you want to make money, you minimize the amount of weight that you are carrying that is not passenger, that is not paying passenger. Really, if they wanted to be smart about it, they should charge according to the weight of the passengers. Then it would be fair. You know, if you weigh 300 pounds, it costs more to fly you to Europe than if you weigh 100 pounds. But okay, let's not waste time in that. So what is the composition of the atmosphere? It is nitrogen, 78%, oxygen, 21%, argon, 1%, a little less than 1%, and then, I know this adds up to 100, so it's a little less than 1%, right? So let me show you the other ones. I'm going to have to erase all this to make room. The other trace gases in the atmosphere are carbon dioxide at 375 parts per million, neon, which is 18.2 parts per million, then there's helium, methane, not methyl, but methane, krypton, hydrogen, nitrogen dioxide, and xenon. So helium is 5.2 parts per million. An interesting fact about helium, you know where we get all our helium? Oil wells. We get it from oil wells because helium is the byproduct of alpha radiation. So when a nucleus emits an alpha particle is basically 2 protons and 2 neutrons, but without the electrons. So it's a +2 charged helium nucleus, basically. It's a helium nucleus without its electrons. But after it loses its velocity, once it slows down, it acquires the 2 electrons, and you get helium gas trapped in areas where there's radioactive substances outgassing for millennia, for millions of years, and slowly the helium content builds up in the oil wells, and then once they drill into it, they can capture the helium gas. But helium gas is becoming a precious commodity bit by bit, because as all the oil wells are tapped out, or at least the top of the well is tapped out, then the helium gas that accumulated over millions of years is released. And once you use helium gas, and it's very often used in cryogenic applications where you need liquid helium to cool things, for example, in the magnets that run MRIs, to achieve superconductivity on the magnets, they have to cool it down to the temperatures that you can only achieve with liquid helium. This is why the next revolution in science is going to be the development of substances that possibly can be superconducting at room temperature, or if they could get to even -50, they could achieve that with a regular refrigerating unit. They won't need things like liquid helium, which is very expensive. Anyhow, methane is 2 parts per million of our atmosphere. Krypton is 1.14. That's a noble gas. It's not just something you hear in Superman. And it's not kryptonite, it's krypton. 0.5, and then finally xenon is 87 parts per million in our atmosphere. Xenon is another peculiar substance. It's a noble gas. They use it for making headlights because it's got lots of electrons, so there's lots of transitions between the different levels of the electrons, so it has a very rich emission spectrum. So if you ever see those almost blue headlights on cars, it's because they're xenon headlamps. They emit a very bright blue light. And the other cool thing about xenon is it can be used as an anesthetic. If you breathe it in, it acts as an anesthetic. It can put you to sleep. It can operate on you, but it's a very expensive anesthetic. I don't foresee that they'll ever be using it that way, but it's known to have anesthetic properties. Okay, so this adds up to less than 1%. Obviously, the CO2 levels are believed to be rising. There's a whole camp of people in meteorology who are running around like Chicken Little saying the earth is going to warm up and we're all going to die because the CO2 levels are rising. Well, I got news for you. CO2 levels in the past of the earth's history have been much higher. If you go to the Carboniferous period of the earth's history, CO2 levels were much higher, which is probably why the earth was covered in greenery. It was very supportive of plant growth. Because let's face it, carbon dioxide is plant food. That's what the plants eat. You know how the trees grow? They take carbon dioxide out of the air. All the carbon that you see a tree being made out of was at one time in the air. What do trees get out of the ground? Well, they suck the minerals. They get water and minerals out of the soil, but the carbon source is the carbon dioxide in the air. So if this gets too low, plants don't grow as well. And it's already down to 375 parts per million. My thing is, we should probably let carbon dioxide grow as population on the earth grows, precisely because we need more food and we could grow more crops and everything else. And plants grow with carbon dioxide. And carbon dioxide levels on the earth has been as much as 15 times higher than what they are now. So let's not panic only about CO2. There are probably other issues that drive climate change. And again, climate change is at the end of the world. Climate change has been happening for literally every ice age that we've had in the past million years. And the cycle has been basically 40,000 years of ice age, followed by about 10 to 12,000 years of warm period. Right now, we've been in a warm period for close to 12,000 years. So in fact, we're actually due for an ice age. So go figure. Let's look at the first practice example where we do a calculation using parts per million as our subject matter. So the practice exercise asks, the concentration of carbon monoxide in a sample of air is found to be 4.3 parts per million. What is the partial pressure of the carbon monoxide if the total pressure is 695 torr? So you remember, we just finished doing that chapter, but normal atmospheric pressure is recognized to be 760 millimeters of mercury, or you could say 760 torr, or 101.325 kilopascals, or 101,325 pascals, or 1.01 bar, or you can say 1 atmosphere. So practice example on page 772. You have 4.3 parts per million, which means you have 4.3 moles of water. Is that what it says? Did I do the right one? I put water. It's not water, it's yellow. Calculation is right though. And 10 to the 6 in 10 to the 6 moles of gas, which is the atmosphere, air. So that gives you 4.3 times 10 to the minus 6. And if you multiply that by 695 torr, which is the pressure of the whole atmosphere, so this is a mole fraction right here. Remember partial pressures? When you find the mole fraction and you multiply it by the total pressure, you get the partial pressure of that gas. So what we get for the partial pressure of carbon monoxide is 2.9885 times 10 to the negative 3 torr. Something you should know about carbon monoxide, you don't need a very high partial pressure for it to be dangerous for you. Now I can convert that to millitorr. There's 1,000 millitorr in 1 torr, so what you get is 3 millitorr. Carbon monoxide sticks to your blood 200 times better than oxygen does. Oxygen is 21% in the atmosphere, so basically you only need 1/200th the concentration of carbon monoxide in the air for it to effectively compete with the oxygen. So if you're in an atmosphere that has even just 1% carbon monoxide, that's quickly going to become lethal, because you'll breathe it in, it'll displace your oxygen, and before long you'll find yourself panting. But that's not going to help, because if you keep panting in an atmosphere that's 1% carbon monoxide, you'll absorb more carbon monoxide. The usual treatment for carbon monoxide poisoning, if they can do it fast enough, and that's the problem, is to get you into a hyperbaric chamber. So what they do is they put you inside a solid metal container, and they raise the pressure so that you get like 10 atmospheres of oxygen for I don't know, a few minutes or hours, whatever it takes to push the carbon monoxide off your blood. They can also give you some medicines that help to unbind the carbon monoxide from your blood so your body can get rid of it. But carbon monoxide is a very dangerous substance because the poisoning sneaks up on you. You start feeling tired and yawning a lot, and then before long you feel like falling asleep, and if you fall asleep, you never wake up. I'll do one more, and then we'll call it a day. On the next page it asks, in the practice exercise, okay, well this is related to, it's called photodissociation. So it's an important thing in our atmosphere. Our atmosphere protects us from the sun. The sun emits radiation that would kill us if it wasn't for the fact that we have, one, a magnetic field on the earth, and we have an atmosphere. So both of those two things protect us from the sun, because the sun shoots out particles and it also shoots out radiation that's too intense for life. So the particles are dangerous because they come flying at us like bullets, going 400 kilometers per second. They still take a few days to get here from the sun's surface, but when they do reach the atmosphere, before they even reach the atmosphere, they start to hit the Earth's magnetic field. Unfortunately, a lot of these particles are charged, so what happens is they sense the magnetic field lines and they start to curve according to the magnetic field of the Earth. And they end up going to the North Pole or the South Pole. So they sort of hit the Earth's magnetic field and they bend around it, and they end up coming in perpendicular to, or close to perpendicular to, the North Pole or the South Pole, and that's why you see the aurora borealis. That's where that comes from. It's all these ionized particles coming from the sun, rocketing through the cosmos for several days, going 400 kilometers per second, and when they hit the gases at the outer reaches of the atmosphere, they literally knock electrons off the atoms. And then the atoms, when the atoms are ionized that way, they emit light. So when the electrons fall back into their ground state positions, they emit the energy they absorbed from the photons, from the particles emitted by the sun. And that's how you get this green glow in the sky. It looks like curtains ruffling in the wind. It's caused by particles from the sun hitting the molecules in the upper reaches of the atmosphere. I think green is caused by oxygen and red is caused by argon. I can't remember which one is which, but you get red and green mostly. Yeah, I wanted to tell you that the magnetic field that the Earth has is the reason we still have an atmosphere after 4.5 billion years. If we didn't have our magnetosphere, that's what it's called, the magnetic field around the Earth, if we didn't have the magnetosphere, the sun would have kicked atoms off the top of our atmosphere, because when they come in, those high velocity particles come in, it gives them energy and it shoots them off into space. But thanks to the magnetosphere of the Earth, they don't come in at an angle, they don't come in tangent, they come in perpendicular, so they tend to knock the particles downward. So it actually creates a transfer of energy, but in a downward direction. So typically you won't lose the gases that compose the atmosphere, because if we didn't have a magnetic field, then those particles would come in and they would hit the Earth's atmosphere at a tangent, and a lot of the gases would get kicked off into the outer space. And eventually, over the course of literally billions of years, the Earth would have lost its atmosphere, as happened to Mars. That's probably what happened to the planet Mars, because if you look at pictures of Mars, you see evidence of large bodies of water, flows of water in the past, in that planet's history, and then now it's just like an arid desert. So sometime in the past, probably Mars had a pretty solid atmosphere with water and rain and clouds and everything else, but over the course of ages it lost its atmosphere due to that effect of the sun kicking molecules off it, because it's a smaller planet with a lower gravity, and it apparently does not have anywhere near the magnetic field that the Earth does. So it has none of that protection that the Earth has. So the Earth is in a very particularly sweet spot. Not only does it have the right distance so that water stays liquid, it has an atmosphere with just the right composition. It has a moon that keeps it anchored so it doesn't wobble when it's turning, because if the Earth wobbled, if it precessed, whenever you have something spinning, it can also precess. And if the Earth precessed, it would wreak havoc with our seasons. We would have summer, winter, fall. We would have like summer for 2 weeks and then winter for 2 weeks, and it would just be impossible for anything to grow. So the set of circumstances that gave us climate on the Earth are perfected, it seems. It seems contrived. That's how perfect it is. So anyway, we're going to explore the notion of photodissociation. That is the idea that high energy rays from the sun actually break down molecules in the upper parts of the atmosphere. And that's part of chapter 18.2. And we'll pick it up from there tomorrow.